Kristen, yay. Faithful Kristen's online.
Yes, hi, Professor Griffin. How are you?
Doing great.
Okay, I actually wanted to ask you something as far as the strengths, since it's
Sure.
just me and you here and it's early still.
Yeah, go ahead.
Okay, so on the problem F8-2, like I guess I was just confused on how to make. So what I found for the tau is that my tau XY for the Moore circle when I, solved the equation and stuff for
Yeah,
the for the to find the tau I did the VQ over IT.
yeah,
So is that going to be my tau X, what my tau XY is for the circle?
yeah. And I believe it's going down on that particular problem, if I remember. And it's VQ over IT.
Right. So that is my okay. And I found a sigma, using the my over I.
Right.
Okay. But is that my sigma X or my sigma Y? And whichever one it is, which is my other one?
Now that one's going to be sigma X.
Okay, then how do I find the sigma Y
I hate to
then?
lie. I don't want to lie to you, but I don't think there is a sigma Y.
Okay, so then
I
how
think
do
I
I
think
go about doing the circle?
it's got tension, right? Or
Okay,
is it?
no, I found that it was in compression.
Well, dang, I need to.
Like I said, normally we have the other values, and we
Yeah.
have the three values to do
Hey,
the circle.
I got to go get my notebook.
Okay, thank you. I'm sorry.
That's fine. Don't go away.
No, I'll be right here.
I'll be right back. Okay. Now, Kristen,
Yes, sir.
let me pin my video thing up here. Oh, we have Dawn too, and we have another customer. Kristen, Kristen and I are talking about another class, so don't pay any attention to us.
Hey, you're good, sir. I'm just getting everything set up.
Okay. Kristen, which problem was this?
F8-2.
Yeah, okay, uh-huh. All right. F8-2. Okay. Just a minute here. Totally organized as always. What page is it on, Kristen?
F8-2 is on page 430, sir.
430, okay. All right. Well, you're going to have a shear force on your left-hand member going down, wouldn't you? So you see that 400 going down on the
Yes.
end?
Yes, sir.
You got to have a 400 going up.
Right.
But see, that's going to be on a right-hand member. And so on the left-hand member, you'd have a 400 going down. So you'll have a shear force going down and you'll have a bending moment.
Right. So wait, I have my V is going up. Is that not correct?
Well, it's going up on the right-hand member, but we're always going to look at the left-hand member. See that AA, that what do you call
Yeah, that A dash A.
yeah. What do they call that?
A dash A.
We'll call it A-A. Anyway, you need to always look at the left-hand side, and there'll have to be a force going down of 400 on the left-hand side. If there's a force going up of 400 on the right-hand side of AA, then there'll be a 400 going down on the left-hand side, right?
Well, the 400 is going down on the right hand side. So I put my.
No.
Oh,
There's a 400 on the end of the beam going down.
right.
But at AA, on that little piece on the end there, you'll have to have a force going up. The sum of the forces has to be 0.
Right. Yeah. So I do have that going up.
Yeah.
I have a 400 going up.
Yeah, on the right side of AA, but on the left side, it'll be going down. Newton's third law said so.
Okay.
Does that make sense?
Yeah. But then I guess like I said, I just on the circle, I mean, what am I using for sigma Y?
Okay. I'm still thinking there is no sigma Y, Kristen.
Okay.
Now you will have a sigma X, and I believe it's tension where they have this capital A there, because remember it's tension on the bottom, compression on the top. Well, that's a little bit below the centroid, so that'll be a little, you'll have a little bit of tension there, but there won't be any Y or sigma of Y.
Okay.
Yeah. You're going to have a tau sub XY going down,
Okay.
and you're going to have a sigma of X going to the right on that left-hand side. It's confusing.
Okay.
But there will be no sigma Y.
Okay. I just want to make sure because I wasn't really sure how to do that circle without like this sigma Y because, normally it's.
Yeah. Hey,
we have
everybody, we've got a lot of Thermo
Okay.
customers.
Okay. Yeah, I'll look at it more later. It's almost done now. Okay. Thank you.
Oh, anytime. Kristen and I were talking about another class, but we're getting some Thermo students logging on. I see Tyler, Levi, Kerman, Jackson, Kristen, and Dawn. We got a good crowd. And we're going to start our Thermo class at 1 o'clock. And I ask you guys to do a refrigeration cycle 965. And I've got the answers up here pretty much for 965. Not all of them. We'll finish it together. I'm going to give you some homework to turn in on Blackboard before we leave today. But this was not to turn in. This was just for your pleasure and learning, okay? And that's the answers on the board to most of it. Let's see what else we're supposed to do. 965. Let me find it here. 965. They wanted the heat transfers. Well, there they are. There's all the heat transfers. Let me put them on the board here. Now, the one that interests us the most, if you have a refrigerator, is this heat transfer here. So see this heat transfer here? This is Q41. That's the removable, you're removing heat energy from your hot dogs and your milk and your whatever you have in your refrigerator, and you're transferring that energy to your I think it's R134A. Yeah, this particular refrigeration cycle is using R134A. So they ask, find the specific heat transfer from the cold space. Well, that's it. That's the specific heat transfer from the cold space. I don't like that word specific heat transfer. I would rather you called it heat transfer per mass. We got some more customers. There's Ross and Jackson. You guys are, and Coy, you guys are so welcome. But there it is there, and it's positive. Where is it? There it is. It's 136.7. It's positive because it's going into your refrigerant. This heat transfer here is negative. Whoops. I'd like to draw those in red if I could. I'm putting the heat transfer here. This is Q23. Q23. And see, it's out, it's warming up your kitchen. The Q23, I don't know if you guys can read that. It's warming up your kitchen, and it's negative. Notice it's negative 170. It's going out of your, in this case, condenser, and warming up your kitchen. What else did they want us to do? Specific heat, yeah, and then to the hot space and the COP. Okay, let's do the COP. Well, the symbol they use is a beta. And this beta is always something you want, something you desire, divided by something that costs you. Well, what you desire is to keep your hot dogs cold, the Q41. So what you do is you put a 136 right here. And the cost is this 33.4. See, that's the little W coming in here. I really like that in red. I don't know if you guys can see red. Never mind, I'll just write it. This is little w 1, 2. It's the work per mass that you need to run this thing, and that costs you money. You got to pay the electric company for that, and that is 33.4. So if you'll divide that, you'll get the beta for that refrigeration cycle, and it is I'm getting 409, 4.09. That's your COP, they call it, coefficient of performance. Now, I asked you guys to finish this. We got some of it done last time, and I finished it. And I'll go over any one of those numbers you want. Just ask me. If you need help with any one of those numbers, look at your paper, look at mine, and if you want me to, I'll go over any of those numbers and how I got them. We have Tyler, Ross, Levi, Kristen, Coy, Kerman, Jackson, Don. Got a good crowd. Would any of you need help on getting any of those? I think we didn't quite finish it Tuesday. There was some empty blanks there.
Can you show us the small? How do you get the small Q for process 4 to 1.
Okay, let's do that. Now Coy wants to know how I got the 136.7. And the way you do that, Coy, is you take the first law. You take the first law of thermodynamics. And, you know, that's the one that starts off dE dt equals Q dot minus W dot plus la, 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 la. That's the first law because this is a control volume. And this is a steady state refrigeration cycle. So you have 0 because there's no change in your energy in your cycle with time, just location. And if you're doing 4 to 1, there's going to be a Q dot because this is an evaporator. See, the evaporator cools off your hot dogs. Just like if you go jump in the swimming pool and get out and that water evaporates, stand in the wind. There's a nice breeze blowing and you're all wet and you feel cold. It may be hot summertime, but if you're all wet and the wind is blowing on you and you just got out of the swimming pool, it feels cold. Well, that's what you're doing. Evaporators remove heat energy from your hot dogs, just like they remove heat energy from your body when you get out of the swimming pool. So that we don't throw that away. That's not 0. And then you have minus 0 because there is no power on evaporators. This is an evaporator. We are doing process 4 to 1. It's an evaporator. They don't require being plugged into an energy source. They don't give you any energy. They don't need any. You didn't have to have any motor attached to your body when you jumped out of the swimming pool to cool off, did you? No, you just got out, you were wet, and it starts to evaporate, and you cool off. Okay, plus m dot times H1 minus m dot times H2. We're going to just neglect the potential energy terms and the kinetic energy terms. If you divide everything through by m dot, your mass flow rate, you can get rid of those. And what you'll have is little q 4,1 equals, now on the algebra, I don't want to screw this up. I think it turns out to be H2 minus, no. We're going from 4 to 1. This is 4. That was wrong. Somebody could have gotten a thank you point. So when we switch it, this will be 1 and 4. So you take H1. I think I'm talking to Coy. I think Coy's the one that asked me. Take H1 and subtract H4 and tell me if you don't get 136. Should be 136 if I did that right. Kilojoules per kilogram. Back to Coy. I think Coy asked me. Coy, are you happy now?
Yes, sir. Yes,
Okay,
Mr. President.
well, good. Next, you're so very welcome. Anyone, if you want me to show you how to get any of those numbers, just ask me. I'm listening.
So for the Q and W, you just use the same equations from the Rankine cycle problem we used?
Yeah.
The second law? Okay.
It's like the Rankine cycle, only it's sort of backwards, isn't it?
Yeah.
See, the Rankine cycle was clockwise. This one is counterclockwise.
Okay, but it's just the same second law equation.
Well, that one's a first law equation.
Oh, first law, my bad.
I'm still listening if you have any other question on the, what is it? It's a refrigeration cycle, yeah. And I think we answered all their questions. Yeah, we did. Okay. Well, we're going to move on to the next wonderful topic here, which is, it's going to be the auto cycle here in a minute. But first, I want to go over an important equation. So I need this. See, I need this space. I'm going to have to say goodbye to this whole thing right here. And here's your last chance to ask me anything on that. Well,
How about little w, 1 to 2?
okay, let's do that. Little w from 1 to 2. Let's do that. Here we go. Thank you for asking. I've got some room right here. I'm just going to erase all this. We don't need any of that. We're going to get little w from 1 to 2. Now, from 1 to 2, that's the compressor. 1 to 2 is the compressor. And the first law of thermodynamics, keep in mind now, it's for control volumes. The first term is dE dt, it's 0 because it's steady state. This compressor has been running for a while. Nothing is changing with time. Now, the heat transfer term is 0 because this is an adiabatic, in fact, it's an isentropic process. You're going to go straight up on your TS diagram. In other words, the entropy stays the same. Look at the entropy from 1 to 2. It stays the same. Okay, so there is no heat transfer. And then you have minus, and this time if you want me to, I can write big letters and then divide by m dot, but if you let me be lazy, I'll just put the little letters in. And so what you'll have, when you get all through and you divide through by m dot and get rid of the kinetic and potential terms, that's it. By Jove, that's it. So little w12 should be h1 minus h2. Okay, now take h1, 392.28, subtract h2, 425.68. See if you don't get negative 33.4. By Jove, I think you do. What you get is negative 33.4 kilojoules per kilogram. Now, what does it mean when you have negative work? Well, see, positive work would be if you had a heat engine that was providing you with work per mass, but refrigerators don't provide you with work. They require you to input work. So you have to plug them in. You've got to plug this thing in, and the work per mass is going into the cycle. I forget who it was that asked me that question.
It was me,
What was it, Dawn?
Kerman.
Oh, it's thank you for asking that, Kerman. Are you satisfied with that?
Yeah, I found my mistake.
Oh, good.
Thank you.
Anytime. Anybody else before we move on? Because if you don't ask me, I'm going to erase this whole thing here. All right. I warned you, I'm going to erase it. 5, 4, 3, 2, 1. Too late. You didn't ask me anything. So we're gonna show you something else now. We're headed towards talking about the auto cycle here in a minute. But first, I want to review a very important equation. And I know you've seen it before, but we better review what the heck is going on with this equation, when you can use it, where it came from. And so I'm going to bore you with some theory here for a minute or two. Now, what that equation is for ideal gases that are in a polytropic process. Hope you can read my writing. Now, if you don't have an ideal gas, just a minute now, let me think. Yeah, if you don't have an ideal gas, don't use that equation, because it's only going to work for an ideal gas that has a polytropic process. If you have an ideal gas and it's not a polytropic process, then don't use it. So let me show you where it comes from. First of all, if you have an ideal gas, then P2V2 is equal to RT2. And P1V1 is equal to RT1. And if it's a polytropic process, then P1V1 to the N is equal to P2V2 to the N. This is called the polytropic condition or the polytropic equation. All right, here's what I'm going to do. I'm going to divide these. And when you do, what you'll get is the R's will go bye-bye. And you'll have T2 over T1. You can see that. And over here on the right, you're going to have, I switched them, but I think you can handle it. Can you make it from here to here? I just divided some equal things, and that's what I got. Okay. Now what we're going to do is follow this. See if you can follow this. V2 over V1 to the N should equal P1 over P2. Can you get from here to here, algebra students? Can you make it?
Yes, sir.
Yay, you can make it. Okay, so here's what we're going to do now. We're going to go V2 over V1 is equal to P1 over P2 to the 1 over N. It's kind of a subtle little math trick. What I did was I took both of these to the 1 over N power. See, if I take this to the 1 over N power, I'll just get 1. Ta-da, see the 1? If I take this to the 1 over N, hey, I get that. So what I'm going to do now is put that up here. And what I have is P2 over P1 times P1 over, that's supposed to be P. I did something wrong. Yeah, it's a P2. There we go. I had something wrong, but I fixed it. Over P2. We're almost done. We're almost done. I might have done this with you before, but I don't think so. I think I just said, hey, look, here's a wonderful shortcut. You can use it if you have an ideal gas polytropic process, and enjoy. Now I'm going to do another little algebra trick here, and I'm going to write that as P2 over P1 times P1 over P2 to the minus 1 over N. That's kind of a subtle little thing. I flip those, but in order to do that, I had to take and make that minus. Can you handle that, algebra students? Hopefully. Yeah, hopefully.
Yes, sir.
Now, wait a minute. Now, I think I've just fouled up here. Just a second. Am I doing this right? I have a bad sense that I've done something wrong. Now, just a second here. No, it looks right. Yeah, it looks right. P1, P2. No, here's where, yeah, I did do something wrong. It was wrong, but now it's right. There we go. See, what I did was I flipped these, but made that minus. Now it's okay. I almost fooled you there. But I think I'm okay now. Now that can be written as P2 over P1 to the 1 minus 1 over n. And finally, is there room? Is there room? Yeah, there's room. Finally, you can write that as P2 over P1 to the n minus 1 over n. Ta-da! We just showed you this one here. We showed you from scratch where that came from. Oh gosh, my wife's got the air conditioner on and I'm freezing. Just a minute, I'm gonna go get a coat on. Stare at that, that's the bottom line. Now I would take time and show you this, but I bet you guys could do that yourself. Let me go get a sweater. I'll be back. This air conditioning is really working good. It's not that hot out there. It's a beautiful day. Oh yeah. Oh yes. I've got a nice coat on now, and I'm going to be fine. I'll be warm now. I don't think I'm going to go all the way and show you this part here. It's just bonehead algebra that I know you guys can do. So let me get rid of all that. Tell you what, and let's start on the auto cycle. I put it on the other side. I just discovered this a few days ago, that you can take this whiteboard and flip it. You can flip it. Shazam! Look at that. It's got a back side. Isn't that slick? And now wait a minute. Okay. Can we see that okay? Pretty good if it'll settle down. There we go. Now we're going to talk about the auto cycle now. I gave you a chance to ask me anything, but I'll give you another chance. Is there any comment or question before we tackle the auto cycle?
What you just went over, sir.
Yeah.
I know that that was stemming from like the ideal gas law and whatnot. For polytropic process, the
Yes.
P1V1 to the N is equal to P2V to the N.
Yes.
I don't know if I'm just forgetting it, but does that particular polytropic equation only work with ideal gas? Not the one that you went over, but
yeah. That's
P1V1 to the N.
That's an excellent question. Is that Ross speaking?
That's
Or
done.
that's Don? It's Don. Okay, Don, here's the deal. Polytropic processes can occur with water vapor. They can occur with refrigerants. They don't have to be ideal gases, Don. You can have a polytropic process. All you got to have is P1V1 to the N is equal to P2V2 to the N, and you got yourself a polytropic process.
Yes, sir.
Got it.
I just wanted to make sure I wasn't missing out on it.
You're not. All right, now we're going to do the auto cycle. Now this happens to be problem 1059, but let's tell you what an auto cycle is. Now they tell you in the book here someplace. Now let me see if I can find it here. Auto cycle. Yeah, here we go. Getting close now. It's in your book. It's on page 314. And the auto cycle is a theoretical cycle for the automobile engine. You've got an automobile engine, most of you, unless you have an electric or a hybrid or a diesel. My car is an automobile gasoline engine. That's what I mean. You've got a gasoline engine. Probably all of you have a gasoline engine, and the auto cycle is the theoretical model for a gasoline engine. Now it consists of two adiabats. These are adiabats. Notice they're steeper than the isotherms. Those red lines show up. Those are isotherms. See, here's the cooler one, and there's the hotter one. But these are adiabats, and they are steeper than the isotherms on a PV diagram. Now these are isocores, constant volume. The auto cycle has two isocores and two adiabats. They have names for all of these. This is called the compression stroke. This is called the ignition stroke. This is your power stroke, and this is your exhaust intake stroke. Now, automobile engines are really four-cycle engines. The physical cycle is got four cycles. They go compression, ignition, power, exhaust, intake, and then they go, I did that wrong. Then the exhaust is a mechanical cycle that goes to here, and then that's the exhaust, and then the intake is going to here. It's really four cycles. See, when what I'm saying is the piston goes up and down, up and down. That's one cycle. It has to go up and down twice. Here, I'll draw it for you. Here comes the piston, compression. I'll draw you a piston. Here we go. Here's your cylinder. Here's your piston. And we're gonna turn this clockwise. Here's your crankshaft. Now, as the piston goes up, they have a intake valve here. No, they don't have any. They have valves here, but they're shut right now. The piston goes up, you have your compression cycle. There's a spark plug here. It gets to the top, the spark plug goes off, bam, explodes, piston comes down. Piston goes back up, and the exhaust valve opens, exhaust goes out, piston gets to the top, exhaust valve closed, piston comes back down. It's going round and round, and the intake valve opens up and lets air in and fuel. You have to have some fuel in too. So you understand the mechanical cycle is 4-cycle, but we're modeling this on a thermodynamic single cycle. And so we're putting the exhaust and intake as an isochore from 4 to 1. Read it in your book. Well, there's the auto cycle, and now we're going to do it. Let's get started, and let me find it here and see what it says. This is there any question on the auto cycle before we get started on this one? Well, it says air flows into a gasoline engine at 95 degrees, 95 kilopascals. Right here at state 1, we're dealing with air in here, and it's at 95 kilopascals. So we're going to put a 95 right there. And the temperature is 300 K. So we're going to put 300 K right there. Oh, hey, it's air, so you can use the ideal gas law. P1V1 equals RT1. We're going to take a minute now, and I want you to find the specific volume at state 1, and I will too, and we'll put it in there. On your mark, get set, go. You do it. I wonder if I got that right. Did you get 0.9063 cubic meters per kilogram?
Yes, sir.
Yay, good going. So we're making progress. Now let me keep reading here. If anybody tuned in late, we're talking about the auto cycle. It's got 2 isochores and 2 adiabats. And we're doing problem 1059. And it says, air flows into the gasoline engine. It's compressed with a volumetric compression ratio of 8 to 1. Let me tell you what that is. That's the compression ratio, and it's V1 divided by V2. See, here's V1 right here. That's V1. Now V2 is right here. And they said that it's 8 to 1. The compression ratio is 8 to 1. So we can get V2, just divide that by 8. We got V1 divided by 8, and I get 0.1133. 0.1133 cubic meters per kilogram. Double check it on me, make sure that's right. Now you have 2 isochores. Does anyone remember what an isochore is? See, 2 to 3 is an isochore.
Constant V.
Constant V. So guess what? I know what the specific volume at 3 is. It's an isochore, so it's 1133. It stays the same. It's an isochore. Did I do that right? Yeah, I did that right. See, remember when the piston gets up here to the top, they have a name for it. At state 3, they call it top dead center. TDC, top dead center, is at state 3. And the specific volume is the same as it was at state 2. Did I say that right? Let me think now. Let's see. Yeah, I think that's right. State 2 is top dead center. Now state 3, you got the same specific volume, but the temperature is different. Do they tell you what it is? Let me read it. In the combustion process, 1,300 kilojoules per kilogram is released. Well, I can tell you what that is. See this Q23 right here? It's, did they say 1,300? Is that what they said? 1,300 kilojoules. Well, I already wrote kilojoules per kilogram. 1,300, that's the fuel. See, they're burning that fuel, and that the air in that piston with the fuel gets real hot. And guess what happens? Well, it's going to expand and it's going to push the piston down in the power stroke. This is the power stroke. And by the way, we can get this specific volume at 4 because 4 and 1 have the same specific volume. So this is 0.9063. Do I need to explain that to anybody? You guys are okay with that? Okay, well, we made a great start. Let's fill in some more boxes here. On your final exam, you're going to be given something like this with a bunch of empty boxes, and you're going to have to fill them in. It's not hard. Well, let's show you how to. Let's show you how to get maybe P2, for example, or T2. I need some room to operate. Hey, I got some room up here. Let's use that. I see some room up there. Back to this equation that I was giving you a little talk about earlier. Well, now wait a minute. I didn't tell you about this equation here. This is different yet. It looks just like the other one. But the one we just talked about, that was a polytropic ideal gas equation. Now we got an ideal gas. Air is an ideal gas. And it turns out it is polytropic, but it's a very special polytropic equation going from 1 to 2. See, 1 to 2 is an adiabat. In fact, it's a isentrope. And I think I showed you this equation. This equation is derived from this equation here. I started this and derived it for you. You might have slept through it, I don't know. There's that one, and there's another one that goes like this. Now, these equations are in your book, and I derived them one day for you while you slept through the derivation. And if you put a 0 right here and do some algebra, you can get this equation here. If you put a 0 right here and work with that, do some algebra, you can get this one here. You can get the whole thing with these two equations. Now this K here is C sub P divided by C sub V. Now for air, you all know, you memorized this. It's 1004 divided by 0.717. It's 1.4 for air, but be careful for other things. It's different. Like if you were dealing with helium, for example, this is different. It's got a name, by the way. It's called the specific heat ratio. That's the name of it. And we're going to use this equation to find, we're going to find T2. So here goes. T2 is to T1, which is 300. I'm going to use this one as 8 is to 1.4 minus 1. See, V1 over V2 is 8. That's called the compression ratio. Hey, look at here. We got a nice equation and we can get T2. I'm going to do it. You do it. I'm going to do it. See what you get. Hey, I got my answer. I think it's 689.2 Kelvin. But I want to hear a couple of uh-huhs.
Yes, sir.
There's one.
Yes, sir.
Yay, there's two. And while we're at it, you could use this equation here to get the pressure, or you could just use the ideal gas law. Well, why don't we use the ideal gas law? Go P2V2 equals RT2. See, we have T2 now. We don't need to use that to get P2. On your mark, get set, go. Okay, I'm doing that now. Well, I got an answer. I'm getting, I think I'll round it off to 1746. You know what I bet? I bet that's 8 times as big as 95. Let me see if it is. No, I'm thinking wrong. I am thinking wrong. But I think I got the right answer. Why was I thinking 8 times? Oh, I think that would be what the situation if you had an isotherm, but we don't have an isotherm. We have an isochore, don't we, from 2 to 3. Okay, we're doing great. Now what? How about you guys? Do you have any suggestions? We got to fill in these boxes. How about this? 2 of these Q's are 0. Which one of those little Q's are zeros?
1 to 2 and 3 to 4.
Yes, 1 to 2, 3 to 4. Now 2 of these little W's are zeros. Which ones are they?
2 to 3, 4 to 1.
Good going. Hey, that's worth a couple of points there on your final exam. Each one of those is worth some points. That was easy. Now, what about some of these other boxes? Any ideas?
You also said there was 2 adiabats.
Yeah, there's 2 adiabats. Well, we got the zeros for the adiabats. Do you have any ideas on those adiabats?
What I was meaning is, if it's adiabatic, wouldn't we be dealing with 95 and 1746 as well on the other 2 pressures?
You might be.
Let me make sure I'm not thinking wrong here.
We got the 95 and the 1746, but that's Don speaking.
Oh, I'm losing my mind. Don't listen to me.
How are we going to get these?
My brain went sideways, and for some reason I was thinking adiabatic was changing pressure. I'm losing my mind. Isobar.
Well, now there are no isobar. There's no isobars on this deal. I don't see any isobars.
I was just thinking wrong.
Okay, that's fine. Maybe we all do that. We got some missing boxes here. And I want you to give me an idea to find them. Here, I'll make some space for us in case we come up with any great ideas.
I know there's an equation for solving for the delta U, and it's like,
Yeah.
but I can't remember. Looking at my notes. Is it like CP delta V or something?
Yeah.
Maybe.
Oh,
Oh my goodness! I remembered something.
You are so close, but it's
Oh.
CV. It's
Would
not
it be-
CP.
Oh, CV. Okay.
It's CV
Well,
delta T. So
okay.
we could do that from 1 to 2. Let's do that. From 1 to 2, that's for air, it's 0.717. This was a good idea. And now what is the change in temperature going from 300 to 689? It's 389, isn't it?
Yes, sir.
389.2 Kelvin. All right, do that, and we'll get the delta U there from 1 to 2. Here goes. Did you get 279? 279. I like it.
Yes, sir.
Hey, we're making progress. Now look at here. We're dealing with control mass here. It's a piston cylinder deal. And delta U is equal to Q minus little w. And we know delta U and we know Q. So what's little w?
279.
Yeah, plus or minus 279. Which is it?
Minus?
Yep. How'd you know it was minus? I guess the algebra.
As
The
you work the equation, you'd have to get a positive W, and you'd end up with a negative 279.
Yeah. Another way of thinking about it is you're compressing. Have I ever told you that compressing, we're doing from 1 to 2 now. Have I ever told you compression work is negative? Have I ever said that? Compression is negative work?
Yes, sir.
Oh yeah, I've said that. Compression is so it's negative. Hey, look at us. We're doing great. Well, we got some more boxes to work on. You guys did great. You came up with a couple of more ideas there, but I'm still listening. I hear nothing.
Can we not get the delta U for 2 to 3 by just using the same one we just did, except for now we have a Q instead of a W?
If we only knew this temperature right here.
No, I'm saying like for delta U from 2 to 3, can we not do delta U equals Q minus W?
Oh, that's
to get
good.
that delta U?
Oh, that's good. Oh, that's good. I like that. We're going to go delta U from 2 to 3. Q from 2 to 3, little w from 2 to 3, and we're just going to do algebra. So what would delta U be, Kristen?
Because we don't, there's W0, Q is 1300.
Yeah.
Oh, so yeah, it'd be, I guess, negative. Yeah.
What would I put right in here?
Just 1300.
Yeah, it's just 1300, isn't it?
1300. Good going. Proud of you. Good going. Well, I think we can get this temperature here
Find a
now,
temperature.
because see that 1300 delta U from 2 to 3 is equal to the 0.717 times, why don't we call this T3? That'd be a nice name for it. It'll be T3 minus T2, which is 689.2. And we know what this is. It's 1300, right? So we could solve for T3. Go for it. Find T3 for me.
2502.3.
You're too fast, so I'm working on it. I got 2502. I got 2502.3. Isn't that what you just said?
Yes, sir.
Good going. That was very clever, Kristen. That's not how I did it. Let me show you how I did it, but your way is just as good as mine. But let's do overkill here. Let's show you another way to do it. But that was very clever. I didn't even think about doing it that way. Now here's what I was thinking about. Going from 3 to 4, T4 over T3 is equal to P4 over P3, K minus 1 over K is equal to V3 over V4 to the K minus 1. Oh, we were going from 2 to 3, weren't we?
Yes, sir.
Yeah, well, here, let me redo this. Okay, now here's another way to get that 2502 thing that we came up with Kristen's idea. Let's say we didn't know T3, but we do know T2. It's the 689.2. And see what this is, I think is 1/8. Remember, it's 8 over 1. V4 over V3 is 8 over 1, but V3 over V4, V1 over V2 is 8 over 1, but V2 over V1, well, now wait a minute. Now there's something bad happening here. This is just a 1. That's just a 1 there. Never mind that. No. No, you can't use this equation here. Oh, that's all a bunch of bull. Sorry. I got mixed up. Going from 2 to 3, that's not an adiabat. And you can't use that little K thing. That little K thing, what do they call that? The specific heat ratio? That's for the adiabats, the isentropes. I was going to show you another way to get this 25, but we can get it this way. Now watch this. I was doing it right the first time. This is an adiabat from 3 to 4. So you can go T4 over T3. Yeah, but we're not supposed to know either one of them, are we? Just an idea. P4 over P3 equals V3 over V4. This is the K minus 1 over K. And this is K minus 1. Hope you can read my writing. K minus 1 over K. K minus 1. Now let me see here. We're not supposed to know T3 or T4. Kristen got it for us. It was clever the way she did it. But we don't know P4 over, we don't know that either. We do know this. V3 over V4, I know what that is. I think it's 1/8. But it doesn't do me any good. Wait a minute. Don't we know T3? No, we're not supposed to know it.
You bounced ahead again, sir.
Say that again.
You bounced ahead again. You were explaining another way to go from 2 to
Yeah,
3.
I was trying to, but I bombed out. I don't have another way of doing it yet.
Okay, so you shifted forward to 3 to 4.
Yeah.
Okay.
That equation's good, but see, we don't know T3, we don't know T4, we don't know P3, P4. So it doesn't do us any good. So let me think about this a minute. I guess we're going to have to do it the way Kristen did it.
Thing for
Yep, we're going to do it the way Kristen did it.
V4.
Good going, Kristen. But now look at here. We do know T3. Let me circle it. And I know what this is. That's 1/8, right? Yeah. So we're going to get our T4 now. Here goes. T4 over, you have to do it Kristen's way, over T3 equals 1/8, 1.4 minus 1. Okay, now do that with me and we're going to get T4, go for it. Okay, here goes. I'm getting T4 is 1089. How about you guys?
Yes, sir.
That's this hot temperature. This is the 1089 Kelvin. That's pretty dang hot. But you know, when you burn gasoline and it explodes in there, it gets plenty hot. And that expands the piston. And now, aha, look at here. We can get these P's because P3V3 is equal to RT3. So I'm going to go ahead and get P3. Go ahead and do it with me. Let's see what we get.
Just so we know for future questions and possible test questions, like right now, we're going to use the R for air, even though what we're doing is kind of air mixed with burnt gasoline.
Yeah, this is called an air standard auto cycle, and we're pretending it's just air. Now, the truth of the matter is it's not just air. It's got some gasoline in there. But we're still treating it as if it was just air.
Okay.
Okay, now I'm finding this pressure. Here goes. I'm doing it now. Okay, I've got a pressure there at state 3. Now that's the highest pressure. I'm getting 6. I'll round it off, 6,339. So we've got the highest pressure there. Now we can get this pressure here because P4V4 is equal to RT4. We can do that. Go ahead and get that for me. If you need me to do any of this, just speak up and I'll put it on the board. Well, I got an answer here for the pressure at 4. I'm getting 344.9. 344.9. Well, great. Let's see if we can't finish this thing off here. We need this delta U right here. You know how to get it. That delta U is going to equal CV delta T, and we're going from 3 to 4. 3 to 4. So we're talking about 0.717 times T4 minus, wait a minute, yeah, we have these. It's 1089 minus 2502.3. Oops, there we go. Okay, let's get that delta U from 3 to 4. Here goes. I don't know if I did that right. Yeah, I'm getting an answer. Did you get a negative 1013?
Yes, sir.
Well, what does that mean from 3 to 4? Hey, you got colder. See, when you get colder, the change in your specific internal energy is negative. That makes sense. See, when you get hotter, the change in your energy is bigger. It's positive. You get colder, it's negative. Kind of makes sense. Hey, looky here. We can get the work done going from 3 to 4. See, the way that works is delta U from 3 to 4 is equal to the Q from 3 to 4 minus the little w from 3 to 4. And if you know this and this, you should be able to get the work per mass from 3 to 4. What do you think it is?
1013.
I do too. I think it's 1013. We're doing great. Now let's get this one here. How do you do that? Well, that would be the same thing here, only we're going from we're going from 4 to 1. See, we're going to go from 4 to 1, from 4 to 1, and the numbers here will be different. At 1, you have 300, and at 4, you have 1089. Okay, let's get the change in specific internal energy from 4 to 1. Here we go. Well, I got an answer. I got an answer for delta U of a negative. Does it make sense that it would be negative from 3 to 4? No, I'm getting mixed up, guys. What we're trying to do from 4 to 1, right?
Yes, sir.
Yeah, from 4 to 1. So I need the delta U from 4 to 1 and delta U from 4 to 1. Yeah, I got it. Did you get a negative 566 if you round it off?
Yes, sir.
Putting that in the wrong spot. Negative 566. We're doing great. Now, back to the first law. See, this is the first law for control masses. It's a piston cylinder. It's a control mass. It's not a control volume. And delta U from 4 to 1 should equal the Q from 4 to 1 minus the little w from 4 to 1. And if you know that, and you know that, you should be able to get the little Q, the heat transfer per mass from 4 to 1. What do you think it is?
Negative 566.
I think it's negative 566. See, what that is the exhaust. You're heating up Oklahoma, you're transferring heat out of your engine and heating up Oklahoma. There's a heat transfer out of your system of 566. Hey, look, we filled in all the boxes. And now let's answer their question. Let's see what they wanted. This was problem, it's an auto cycle, it's problem 1059. They want the cycle efficiency, mean effective pressure, okay. Now the cycle efficiency, let me make some room here and we'll get that. The symbol for efficiency is this Greek letter eta, and it's always something that you desire over something that costs you. On your automobile, you got to go buy gas. See, that costs you money when you go buy gas. And what you desire, what you desire is this here, the net work. We're gonna find our net work. Let's get that. I'm getting 734 kilojoules per kilogram net work. This should be the net heat transfer per mass. Let's see what that is. 1300 minus 566. Well, Shazam! You know what? The net heat transfer is 734 kilojoules per kilogram. That's because in a cycle, the net heat transfer per mass is equal to the net work per mass. That's one of the earliest, it is the earliest formulation of the first law of thermodynamics. Now, what you desire is this 734 kilojoules per kilogram. But what costs you money, what you have to pay for is this here. You don't pay for this exhaust, but you do have to pay for this because you had to buy gas to burn, to heat up, to burn the gas, to heat up your piston, to give you a expansion. So that's 1,300. And now we're going to get the efficiency. Here goes. I'm getting 0.5646, call it 56%. I wonder if that's what I got when I did this before. Let me see. Yeah, that's it. That's you're not going to get that with your car. This is an ideal auto cycle. There's no friction. There's no irreversibilities. Everything is a reversible process. So it's sort of make-believe. But theoretically, that's what you got. Now, they also wanted the mean effective pressure. I've never told you what that is. Now would be a good time. This is called the mean effective pressure we just about ran out of room there. The mean effective pressure and if I just had some room to work, I could go up here and do it up there. There's a little bit of room here. Now, I know the formula for mean effective pressure, but I'd kind of like to explain it to you where the heck it came from. The mean effective pressure, the formula is the network divided by the delta little v. And let me see if I can explain where that comes from, and then we'll plug it in and get it. You all know that work is equal to force times distance. Force times distance is work. You all know that. You also know that force is pressure times area. See, pressure is force per area. If you take force per area and you multiply by area, you'll get force. So the work you do is pressure times the area of your piston times the displacement or the motion of your piston. You know what that is? That's P big V, isn't it? Well, see, that's a big W there. Now, if you wanted little w would be P times little v. Okay, well, that kind of makes sense. P times little v. Now, what am I getting at? I'm trying to show you my mean effective pressure. And we're going to define this. If you did a little algebra here, can you get to that P is equal to little w over little v? Yeah, you can get there. Well, they're going to define this mean effective pressure, call it MEP, as the network over the change in your specific volume. It will not give you the average pressure. If you wanted the average pressure, you would have to add these up and divide by 4. Let me do that and show you, and then we'll get the mean effective pressure. 95 plus 1746 plus 6339 plus 344.9. Then you divide by 4. I can tell you what the average pressure is. The average pressure in this Otto cycle is 2131 kilopascal. Okay, now we're going to get the mean effective pressure. I kind of gave you a hint of where it came from. Maybe that makes a little bit of sense. But see, we got 734 kilojoules per kilogram. And we got to find the difference.
That says 334.
Thank you point goes right here. Is that the first thank you point of the afternoon? You mean I've worked all this time without screwing up? That doesn't happen very often. Now, you're absolutely right. 734, and then you're going to divide by the difference between these two here, between 1 and 2. Here, I'll write it out for you. 0.9063 minus 0.1133 cubic meters per kilogram. And the units are going to come out in kilopascals, you know it? But here we go. I'm going to do it now. 734 divided by 0.9063. Hope you can read my writing. That's 9063 minus 0.1133. I'm getting 925.6 kilopascals is your mean effective pressure. Now, the highest pressure is actually 6,000 and something. But see, it only occurs for just a fraction of a second, right when the piston's at the top dead center. The lowest pressure is 95. That's when the piston's at bottom dead center. The average pressure is 2,000 and something. But that's not what they call the mean effective pressure. The mean effective pressure is 925. If we did that right. Did anybody get that? Did I do that right?
That's what I got.
Yeah.
That's what I got, sir.
I bet that's right. See, that's what they use when they decide on how tough this engine's got to be. You'll discover we're going to do a diesel cycle, and you'll discover that diesel cycles have a bigger mean effective pressure. That's how come they have to be bigger engines. They can't, we don't want them to crack or anything. So that's how come they have to be bigger and tougher. They have a higher mean effective pressure. Well, we had a lot of fun doing that auto cycle. And I need to give you some homework to do. And I need to give it to you on Blackboard, on your, what do they call it, your content. But I don't know whether I should give you another auto cycle or whether we could move on to a diesel cycle. Diesel cycles are very similar. Let's do a diesel cycle. Okay, we're going to do a diesel cycle. Let me dig around here. Don't have a whole lot of time left. Totally organized as always. Yeah. Okay, here we go. I know what I'm doing now, theoretically. We're going to show you a diesel cycle, and we're going to give it to you for homework, and I'll assign it. But we need to fill in boxes on our diesel cycle. There we go. Now we could get a few boxes filled in before we leave each other today. Oops, I don't want to erase that thank you point. Yeah, now the diesel cycle is going to be different. And this one's going to be 1074. 1070, yeah, that's the one we're going to do. And I'll start you off and fill you in a few boxes. And this is going to be your weekend homework. But it's going to look different. $10.74 diesel cycle. And this is going to be your weekend homework. And I will put it on Blackboard under content. It'll be official. I haven't done it yet, but I will. But you need to know what the diesel cycle is. And it's like this. We don't put a vapor dome because we're dealing with air again. That's true, there's some diesel fuel in there mixed with the air. That's what burns. But the diesel cycle has 2 adiabats, an isobar and an isocore, and it goes like this. It's got an adiabat from 1 to 2. From 1 to 2, it's got an adiabat. And do you remember adiabats are steeper than isotherms? So you're going to have an isotherm through there like that. But see, that's an adiabat, and it is steeper. There it is. Now what this is the compression stroke. And then there's a burn, an isobaric burn. This is the compressive stroke. You could call it ignition, but I think they call it the burn. And you get some power out of that, but the main power stroke is right here, like that. And then this is state 3, state 4. This is part of your power stroke here. Here's your exhaust intake. It's an isocore. So here's what you've got. You've got 2 adiabats. See, Q is 0 here. Q is 0 here. The hottest temperature is right here. This is your hottest temperature in your diesel cycle. But see, it's a little different. It's got 2 adiabats and an isocore. That's just like the Otto cycle. But what's different is it has an isobar. That's an isobar. You can read about it in your book, but we're going to fill in a few boxes, and I'm going to turn you loose on it because we're going to run out of time here. All right, we're doing problem 1074, and here's what it says. It says, the state before compression is 95 kilopascals. That's state 1, 95 kilopascals, 290 Kelvin. You see that isotherm right there? That's a 290 Kelvin isotherm. And hey, you can get little V1 because P1 V1 equals RT1. I know you can do it. You don't need me to do it. It has a peak pressure of 6,000. Do you see this State 2, the pressure there is 6,000. And you see the state 3 has to be 6,000 also, because it's an isobar, it's an isobaric burn, and a maximum temperature of 2400 K. You see this isotherm here, the hot one? That's 2400 K. Now we're going to put that at state 3 right here, 2400 K. Oh, looky here. If you know the pressure and the temperature, you can get the specific volume there. Yeah. But now let's see if they give you anything else. No, they didn't. Now they talk about a cutoff ratio, a compression ratio. Well, let me tell you what those are. The compression ratio is V1 over V2, just like it was for your Otto cycle. They have another ratio called the cutoff ratio. And gee, I forget what that is. I don't want to lie to you, so let me look it up here. This is
It's on for page 318.
Thank you so much. Thank you so much. 318. You're on the ball there, Coy. 318. Okay. 318. Okay. It's V3 over V2. The cutoff ratio is V3 over V2. It's just V3 over V2. Okay, we got that. All right, excellent. Now let me keep reading. 1074. Got lost. The thermal efficiency. Well, you know what that is. We've talked about. It's the same thing. It's the what you desire. What you desire is when you add all these up over here, you're going to get your net work. And you're going to have to divide it by what costs you money. Now, what costs you money is right here. That's going to be your diesel fuel that you're burning. Well, we got a lot of stuff to fill in there, don't we? Wow. Well, see what you can do, and we'll go through it. It's going to be due Sunday. Let's see, today's Wednesday, right? I guess Sunday night.
Today's Thursday.
No, yeah. Today's Thursday. Today's Thursday. Sunday night, midnight. If you get it done before, then I could get them graded. And if you can turn them in late after that, you still get some points. But I'll put that in the content page there. Your job for your homework is that, and I'll put it under Blackboard for you. Before we adios, and welcome all you wonderful students. Ethan's here, Jesus, Ola. We've got Daniel, Mark. We got Mark. Got a good crowd. Before we say sayonara, does anyone have any comments or questions?
No, sir. Have a good weekend.
I will. Best of luck on that diesel cycle, but we'll go through it. But I'll give you some points for it too. You turn it in. Okay. Go ahead.
Could you say the names of the strokes again?
Yeah. This is the compressive stroke.
Okay.
And this is in the Otto, it was the ignition, but they call it the burn because it's sort of a slower burn instead of an explosive. Well, I don't know. diesels make a heck of a bang when they go by. So I don't know, it makes a lot of noise. But that's, you're burning diesel fuel. Now this is the power stroke. This is the exhaust intake. You still have exhaust. Diesel engines have exhaust.
Okay.
Anybody else? Well, that was fun. See what you can do with that diesel cycle, and I will see you on Tuesday, I guess, right? Yeah, Tuesday. Okay.
Thank you, Professor.
Bye.
Thank you. Bye-bye.